Okay, so let's start with the find shortest path. Inside the GeoNode, create a grid and a remesh. The remesh here is useful because now we have a much more interesting edge topology on the surface. So let's create the find shortest path. And let me activate the keep original geometry. So we can specify a starting point. There is nothing magical here. I just took note of the point numbers before starting. And now we have a line. Let me create maybe a color node here. And inside the find shortest path, I can activate the, I don't need this one, the path group here. So we now have a group that we can use. Okay. Now we have one starting point and one end point, but we can also have multiple endpoints like this one. And to see the result, we have to select the option for any start to each end. Now we have 3 lines. But what I want is a little different. I would like to have one starting point and few endpoints. And then another starting point and few endpoints, and so on. So to achieve this result, we cannot use this option, because if we add another starting point here, the node automatically selects the best possible solution. And the best possible solution obviously is the shortest solution. So to achieve what I want, we have to use the last option here, from each start to corresponding ends. And you see we got an error now, because when you select this option, you must have the same number of starting point and ending points. Let me show you what I mean by that. Now, with this option selected, the node draws a line between the first start point and the first end point, the second start point and the second end point, and so on. So, to recreate the initial situation, we have to repeat the start point 3 times. So, we have for each pair, this one, this one, this one, this one, we have a line. But now we are able to create multiple starting points. I don't remember the numbers, just a second. Okay, 2, 6, 4, 8, and 4, 7, 5. And now we have what we want. We have 3 lines here and 2 lines here. And that's what we are gonna use for our vein system. Basically, we are going to create these 2 strings here in Vex. Let me show you what I mean by that. The tail angle. We will create 2 strings attribute containing the point numbers here. This is what we are going to create in Vex. And then on the find shortest path we can say, let me take, on my Italian keyboard the backtip is impossible. Details, 0 starts and details ends, and we have the result. You see? Now that's the plan. We are going to create the detail wrangle to generate automatically these two strings. Another important concept here is the cost attribute. Right now we have a start point, end point, and the only criterion that Houdini has to calculate the path is the distance. But we can also say that, let's say, in this zone, the cost is much higher. So Houdini will try to avoid that zone, like this or like this. Okay. So let me define a cost attribute on the surface. A triangle. My origin is this one. Let's take the position, point 0 P origin point, and let's define a radius. Okay, now points, near points, basically we are defining a circle around this point. 0 origin pose radius, and for each point in PTS we define the set point attribute cost pt1. So we have maybe we can color the attribute. Okay, here we can increase the radius. See here, now we have cost 0 everywhere on the surface except here we have cost 1. So we can tell the define shortest path to use that attribute. Here in the path cost tab we can say my point cost attribute is called cost. And now you see the lines try to avoid that zone. I can increase or decrease the radius. And this is what we are going to use to avoid our vein system to pass through the craters that we defined in the previous video. Let's now talk about a couple of vex functions that we are going to use later on. They are PCFind and expand point group. So let me start from here. Okay, we need the cost attribute, detail wrangle, and let's say that starting from the origin 0, 0, 0, we want to select all the points around inside a certain radius, float radius. And the origin is 0, 0, 0. We can use PCFind, which returns an array of points. The geometry is 0. The PT group for now empty. I will explain it later. The P channel is P, the position is origin, the distance is radius, the max point, whatever. Now, just to visualize what's going on, in PT, in PTS, let me set the color red. Set point attribute 0, CD, PT 1, 0, 0. Okay, now we can increase the radius, you see? Okay, now the important part here is this PT group. Inside here we can define a rule and ask the PCFine to find only the points that respect this rule. For example, in our case we want to avoid the coast zone here, so I can type at cost less than 0.5. You see? Now the cost zone is excluded from the selection. And this is the PCFind function. Now, the PCFind is useful when you have an origin and you want to search points around that origin. But what if you want to select some random points over the surface without any reference? So in this case, we can use the expand point group, which is quite similar. PTS is equal to expand point group, the geometry is 0, and here we can specify the rule as before, at cost less than 0.5. If we do the same, now we have, in this PTS array, we have all the points over the surface where the cost is less than 0.5. And we will use these two functions here to create the detail attributes for the find shortest path, avoiding the craters or the worm surface. Another topic that I want to cover here is the animation on curve. I have used the same stuff in my previous tutorial, but I forgot to explain what's going on. So I want to do a better job this time. So let me create a curve Bezier. And from the top view, let's draw something. Okay, the sample, and activate the curve view attribute. So we now have the curve view going from 0 to 1 here. So attribute wrangle. Now let me create the attribute and then I will explain everything. Float width is equal to CHF width. We have a time attribute, time, and float energy is equal to fit the curve view from t minus width and t from 1.0 and 0, and the attribute f at energy is equal to energy. Now let me visualize the attribute energy, and let's create the parameter here. Let's say 0.1, and now we have something like this. Okay, so what's going on here? Let me grab the sketchpad. we have a curve with curve view from 0 to 1. We are basically saying, take t, this is around 0.5, and t minus something, and map this interval between 1 and 0. And t is growing over time, so this interval is moving along the curve, because at t equals 0 we are here, and we go along the curve. This is t equal to 0.5 till here, where we have t equals 1. So t minus width is mapped over 1, and t is mapped over 0, and the values are clumped over the curve. So everything after this point is 0, and everything before this point is 1. So we have this behavior. After this point, everything is 0, and before this point, everything is 1. That's the trick. Okay. Now we can say, we can remap the energy now, because we don't want this tail. We want to cut the energy here. So we can say energy is equal to ch ramp of energy. Instead of going linear, we can create something like another point here, and the last point 0. So we have this situation now. And obviously we are using time, so we are at 24 FPS. At 24 we have t equals 1, but as you can see here is not completed yet. Maybe t 1.2, and we have only one cycle. To have more cycles, we can use the modulo function. Instead of float t equals time, we can say time modulo 1.2, and now we should have multiple cycles. You see? That's the concept that I wanted to explain. And we can play with it. We can play with the speed, for example. If we plot, let's create a speed parameter, chf speed. Where is the speed? Yeah. We can multiply the time by our speed. One is the same as before. We can slow down or speed up. And we can also say, instead of starting from 0, we can also shift shift the beginning. If we say float shift is equal to chf shift plus shift. Now at the beginning here is 0, but we can say shift, the beginning is somewhere else, here for example. Now at 0 we have this situation. Let me slow down. Okay, now the last topic of the video is the particle animation along the curve. So my idea is this one. We can scatter a lot of points along the line, okay, and we can blast everything that has energy less than something, let's say 0.1. This is a point group, okay, and now we have these particles here. And now we are going to replicate particles along this line based on the energy value. Obviously, the scatter attribute is crucial here because we have a much better coverage if we increase the value. Okay, so create a detail angle. And few parameters, float radius, amount, and a seed. So basically we are going to create a cloud of points around each one of these points here, of radius, this one, proportional to the energy value. And the amount here is the amount of particles to create for each particle. Let me show you. So P count is the number of points. For int I equals 0, I less the P count, I plus plus, we take the position of the point. We take the energy value, and now we say for int j equals 0, j less than amount, j plus plus. Now the direction is equal to sample sphere hemisphere, no, sample sphere uniform. So basically this function creates a random vector inside a sphere of radius 1. You can take a random value between with seed I and j, and now we can say the direction is proportional to the radius and the energy. So now we have a new point, int pt is equal to add point 0, the position plus the direction, and send point attribute of the new point. The attribute is energy, the new point is pt, and the value is energy. Let me see if it works. Okay. Now, you see now we have something with a radius proportional to the energy value. And maybe we can play with the energy value here. Maybe we can increase the, let me see where it is. Instead of energy, we can use a power 5. Yes, it's more compact here. Maybe 3. Yes. And that's the idea. Keep in mind that these particles are not moving, because we are creating particles frame by frame. So if you need motion blur, for example, you have to use something else, or you have to at least you have to create the velocity vector manually, using perhaps the tangent of the curve. But now we have everything in place to create our vane system. So see you in the next video.